The four horsemen of the universe, responsible for all of creation, from the tiniest of subatomic to the largest of supermassive, creating mass out of nothing or changing it in the most elementary way, responsible for change, responsible for effect, responsible for cause, responsible for all. These horsemen are not horsemen at all, they are the fundamental interactions: gravity, electromagnetism, weak and strong force. Using these four interactions, you can describe every other interaction: friction, tension, drag force, perpendicular stress, strain, spring, coulomb, magnetic, electricity, surface tension, heat. All of them stem from these four. So, what are they? Well, let's go through it one by one. First, we have gravity. Gravity is like the Super Bowl of fundamental forces. That's because it makes us all come together and then crashes us into a black hole. I'm a European, I know what Super Bowl is. Especially important if you're doing astromechanics, classical mechanics, or just anything with mechanics at human or greater scales. That's because, surprisingly, it's actually extremely weak. Yeah, it may seem impressive when a planet is throwing around the moon like a ball on a string, but what you have to remember is that these planets have a mass measured in ronograms, and these moons still look practically stationary, so it's not really all that strong. Like, from 10 to the 29th up to 10 to the 38th times weaker than other forces. But what it lacks in strength, it makes up in sheer simplicity. That's because whilst other forces may require things so complex and intricate that we mostly only see them on subatomic scales, for gravity it's different. Gravity needs mass, and only mass. There is no fancy counter, no complex interaction, just mass. If you have a cube with a lot of mass, it's going to attract another cube with some mass. Simple, elegant, beautiful. Or is it? Because how would we describe this attraction? Well, there are three ways. First, we have magic. Nah, I'm just kidding, it's not magic, it's a force field, which basically means that if we have a particle, that particle affects the other particle using a force field. So in 2 dimensions you can imagine it like this, a plane where the brighter the pixel, the stronger the field. Except one detail: force field is a vector field, not a scalar field, which means that whilst this plane right here is great at representing the magnitude of this force of gravity, what it's missing is the direction. That's because for our left particle, it would go right. For our right particle, it would go left. Except there is one problem. What is this field? Like, okay, I get it, this particle is affecting the other one using force of gravity, but how? There is nothing in between them, no water, no air. In a vacuum, these two particles will still come together seemingly without a medium, so what's causing this attraction? The answer to that is the force field of gravity, or in other words, magic. Witchcraft, sorcery, wizardry, whatever you want to call it, and actually you should get used to this being an explanation. That's because we're dealing with fundamental forces, so it doesn't really get any more fundamental than that. Why does matter cause a force field around it? Well, it's because it's gravity. It's a fundamental force. It's an explanation in itself. It causes a force field just because. Or in other words, magic. Or is it? That's because classical force field is only one of these explanations. There is also the quantized force field. So the quantized force field is like a normal force field, except it's quantized. What does quantized mean? Well, it mostly means that it's a foreshadowing for the next chapter, but to simplify for now, we have a basic quanta. This quanta is like the smallest amount of gravity you can think of. It's like a single pixel of gravity. So every gravity is just a certain integer number of quanta. Right here we have 3 of them. Right here we have 0. Right here we have 7. That's what quantized means. Now, the trick in quantum mechanics is that if we have a quantized field, that means we can think of the field as just particles. So right here we have 3 gravitons, right here we have no gravitons, right here we have 7 gravitons. So to oversimplify for now, you have the first particle interacting with the graviton, the carrier particle of gravity, which then interacts with the second particle, causing gravity. Except there is a problem, once again, with this whole quanta approach, rather the quantum approach, because it's not exclusive to gravity, it's the whole field of quantum mechanics. The issue with gravity and quantum is that gravity is ridiculously weak, and kind of the odd one out of the 4, and thus it's actually really difficult to apply this approach to gravity. Basic idea being, in quantum mechanics, you have something called renormalization, which you can think of as like the quantum mechanical version of taking a mathematical limit, and that sort of breaks with gravity, but that's a story for another time. And then there is one more way to describe gravity. Everyone's favorite, relativity. That's because with relativity we are finally done with force fields. Here gravity is bending space-time, which may sound complex, but here's how you can think about it. If we have two particles and they are both coming together, then they really seem to be moving, right? But let's take a look at this interaction again, this time from the perspective of the first particle. Now you can see that it's not actually moving much. It's the entire world moving around it. From the perspective of the other particle, however, once again, it's stationary, it's not moving. So both of these particles seem stationary from their own perspective, or in other words, their movement is relative. That's where relativity comes from. Okay, so which one is moving then? I mean, they clearly come together, so they have to be moving, right? Well, not quite. You see, relativity says that gravity can distort the space and time around them. So you can imagine like this. We have two particles standing on our fabric of space-time, and we distort it underneath them. Now, this is not quite what's happening, but it's a nice way to visualize how things can stay stationary and still appear to move. Now, out of these three different models for gravity, which one is correct? And the answer is none of them are. These are all just different descriptions of gravity with different accuracy at different scales. Classic for medium, quantum for small, relativity for big. That said, however, the best one would definitely be relativity, without question. It is the theory we currently rely on, and it's exactly for that reason. The most problematic one is quantum, because of the renormalization dilly, and classical is just an old classic. And actually, okay, the quantum theory may seem a bit underwhelming for gravity, but that's only because it seems especially incompatible. But for odd forces, it's much better. And there is one force in particular in which it really seems to shine. And that is electromagnetism. Now there is a lot to say about electromagnetism, so first things first, for electromagnetism we mainly have one theory, that is the quantum theory, so individual quanta. For gravity, the carrier particle was the graviton. Now for electromagnetism, it will obviously be the photon! Yeah, it's light. Electromagnetism in its purest form is just light. Which is why I made that extremely clever pun earlier on. This means that before moving on to magnetism and electricity separately, and electrons and flow of electricity and all that stuff, we'll first have to talk about light. So what is light? Zio cum viderum, I know it when I see it, is a phrase used when instead of describing things we already know in extreme detail, we just take the advantage of the fact that it is a widely known phenomena. In this case especially convenient since light is literally seeing, okay, that's what light is. How am I supposed to explain something as elementary as a fundamental force? When your eyes interact with light to perceive information like red, green, blue, yellow, this light is electromagnetism in its purest form. But where do the colors come from? With gravity it was simple. More massive planet, more gravity. But what makes electromagnetism tick? Well, is the wavelength. You see, light is a wave in which we can measure the wavelength. So for example, light with a wavelength of 380 nanometers would look like this. Yeah, it's really hard for our eyes to perceive. As we drop it, we can finally see some colors and it becomes redder and redder until our eyes can't perceive it anymore again. Now, even though this light may seem like it only differs in colors, this is actually a symptom of something much more important. That is energy. Energy of light is inversely proportional to its wavelength, which kind of makes sense if you consider that for a large wavelength, the light oscillates slowly. For a short wavelength, it oscillates quickly, so more speed, more energy. And what's important in my opinion to remember is that the wavelength of light doesn't mean its color, it means the energy. It's just that our brains, and more accurately the eyes, evolved to interpret this energy as color. Color is life interpretation of light energy, not a property of light. Now this already explains a whole bunch of properties of light, and in this case, yeah, I am referring to the entire electromagnetic spectrum as light, but there is a problem. You see, on the very beginning of this chapter, I mentioned how first things first, for electromagnetism, we mainly have one theory, that is the quantum theory. But so far, I have been describing them like waves. Waves of the electromagnetic field to be exact. So which one are they? Waves or particles? Well, if you've answered waves, then you're wrong. If you, however, said, oh no, electromagnetic waves are the old theory, nowadays we use quantum mechanical quanta, so it must be particles, not waves, then you're also wrong. In reality, the answer is both. Now you might be wondering, MAKiT, how could they be both? And that would be an obvious question. So the basic idea looks like this. We have this thing called the double slit experiment, so a light bulb with a wall with two slits, and another wall. Now if light was particles, then after lighting up the light bulb, we'd expect to see particles go like this. However, if they were waves, then you'd expect them to interfere with each other. Here you can see the right slit in red, left one in blue, and both of them added together will look like this. They are interfering with each other. The higher the frequency, the more complex the pattern becomes, and the pattern on the wall would look like this. So, if after setting up the experiment you get this pattern, this means particles. If you get this, it means waves. And if you perform it in real life, then you get the interference pattern, so waves, right? Well, wait till you hear about the photoelectric effect. So an effect in which you have a piece of metal, when you shine some light on it, the energy of the light gets pumped into the electrons, breaking them away. So you have the energy of the light, this much is dedicated to breaking the electron apart, and this much is turned into movement of the electron. So if the energy is too low, the electrons won't leave at all. You need some basic amount to break them away. And then, the higher the energy of the light, the quicker the electron will go. However, there is something curious you might have noticed with this animation. It's the higher the energy of the light, not the more intense the light, which means that a dim violet light will give electrons more energy than an intense red light. Now, this may not seem like a major thing, but it's basically impossible for waves. That's the kind of behavior you'd only expect with particles. If you'd like to learn more about these two experiments, I have an old video on the channel in which I explain this kind of behavior of light, but putting that aside, what we've basically got here is one experiment telling us that photons are waves, and another one telling us they're particles. So, which one are they? Particles or waves? Well, both. It's called wave-particle duality, and it's actually an amazing example of how quantum world behaves. You see, people really often call the quantum world confusing or illogical, but it's not really. It all makes perfect sense once you realize a simple fact. The quantum is elementary. When it comes to elementary objects, however, there is no answer to the question of like how or why. These things by definition are elementary, so they are the first definition. Just like the fundamental forces have no explanation for their behavior, things like photons are their own reasons. They are the place where we start creating the rules. Anyhow, I just wanted to go a bit more in depth because electromagnetism has the most carrier particles of all carrier particles, but with that in mind, we can finally move on to electrons. Okay, so if we have electrons clouding around an atom and we blast them with photons, then we can knock the electron off. This is the photoelectric effect, and it's a great example of how photons can affect electrons. Another example would be Compton scattering, or my absolute favorite, you can have a photon just vanish into thin air and create an electron and a positron in its place. And okay, this is an absolutely amazing thing. It's about as direct as you can get with energy into matter conversion. It's a demonstration of electromagnetism at its strongest, and it shows that even though energy and momentum have to stay conserved, mass doesn't. This literally starts with no mass, because photons have no mass, only to create mass equivalent to 2 electrons. It creates mass out of no mass. But putting that aside, the point is photons are about as close as you can get to electromagnetism in its purest form. Electrons, however, are just elementary particles, which have charge and magnetic spin, so two things to interact with electromagnetism. And right here would be actually where we kind of separate this into two different interactions, the magnetic and the electric. So first let's talk about the electric aspect of the electron. What is it? Well, there are two things that are important, the charge and the field. Field is just a typical force field, just like with gravity in the first definition. It tells us how powerful the force is. Charge, however, tells you how much something is affected by the electric field. So, for example, if you have a particle with a charge equal to 1 and a field equal to 1, then it will accelerate the particle. If we restart the situation, however, and increase the field 10 times, then the particle will accelerate 10 times quicker. The same goes if we halve the field and double the charge. We're making the field 2 times weaker, but the particle is affected by it twice as much. But what if we restart again, we set the field to something like 100 and the charge to 0? Well, then our particle will not accelerate forward at all. We can set the field to 1,000, a million, and infinity, it doesn't matter. Our particle has no charge, so it cannot interact with the field. Unless you're doing some funky relativity business. So the field moves the charge, no movement. But charge creates a field, so if you have two particles, they will both create a field around them. So a consequence of that would be that they both just push each other away, like this. But that's all hypothetical, so let's get real with electrons and protons. Electrons and protons both have the same charge, or rather charge of the same magnitude. That's because their charges are actually opposite. They both have a charge of magnitude 1e, it's just that electrons have a negative 1e and protons have a positive 1e. There really isn't anything negative about the electron, it's just that by convention physicists set the proton charge to be positive, and by extension electron is negative, which is a horrible choice in my opinion, but that's a story for another time. Now, since they both have opposite charges, these charges create opposite fields, and so instead of pushing each other away, they pull each other together. This is the mechanic that allows for molecules to form, but there is more. You see, when we have a large amount of these protons together, like this, then this amounts to a huge electric field of positive charges. Because of that, electrons will get naturally attracted and dissolved into kind of electron soup between them, causing something called dimetallic bonding. Now, when we try to add another electron, then we can't. You see, this bonding is stable because all the positive charges balance out all the negatives. So if we add an electron to it, then the net charge, instead of being neutral, will become negative. So on average, electrons will end up repelling each other. So yeah, an electron can't really get in. That's why we need to force it in. We add our electron, this time with a field pushing it. And there, the electron ends up in. However, this net charge doesn't disappear, and so if we fit our electron in on the inside, these fields stop them from leaving on this side, but on the other side, it's a different story. There is no field to keep it in place there, and there is a field pushing it out, so it just leaves. And that's actually electricity. Voltage tells you how hard you're forcing electrons in, and amperage tells you how many electrons are moving in per second. That's how we use the electric part of electromagnetism, by having the charges repel each other to create movement, kind of like having a mill next to a river. In reality, it's really difficult to actually break these electrons away, so instead we have some molecules which, when given a proton, emit an electron, and on the other side we have molecules which, when given an electron, emit a proton. This is an oversimplified mechanism, but it's a pretty good visual representation of how a battery works. This is the battery, and this is the cable. In reality, this right here probably wouldn't be a proton, only an ion, but it just goes to show that you don't actually need an electron to move electricity. Yeah, you just need the charge. Or to be more exact, movement of charge. Or to be even more exact, linear movement of charge, which would be different from magnetism. Magnetism isn't linear, it's circular. That is where our spin of the electron comes in. So basically, imagine our electron is spinning. If we have a particle with charge like this spinning, that produces and interacts with a magnetic field. The only problem being, it's not spinning, it's a point. I mean, don't get me wrong, all the math stays the same, except the particle itself isn't spinning. This may be a bit confusing but that's only because of the name. Instead of the name, you can think of it as like magnetic charge or magnetic augmentation, kiting, imaginary turning, whichever you like more. The reasoning here basically being that electrons have a magnetic moment. Magnetic moments can only be possessed by spinning charged particles, so electrons must be spinning. Don't mind the fact that they're not, okay? Trust the physics, not the reality. This magnetic moment causes our electron to be like a tiny magnet with a north and a south pole. Here, I won't over-explain it too much because we all know magnets. That said, when it comes to magnetism, we care more about alignment rather than movement. So you can basically imagine all of these electrons with their different spins. If they're all facing different directions, on a larger scale, we'll see no net alignment. Our tiny magnets will all cancel each other out. If, however, they are on average biased towards a certain alignment, then we will end up with a net. This can happen because of unpaired electrons and be amplified by an electric field or by these electrons aligning with each other to lose energy. Now, one more crucial difference when it comes to magnetism is that it's also dependent on the velocity of the particle. The pickle here being that this x in between velocity and magnetic field isn't multiplication, no, that would be too convenient. Instead, it's the cross product, meaning that if we have velocity going this way, magnetic field going this way, then the total force would go this way. Unless I mess something up. Linear algebra is a confusing mess. Okay, so cool, that's our magnetism and that's our electricity, but why are they a single interaction? Like, yeah, they certainly are connected, but why are they a single fundamental interaction? Well, that's because I've lied to you, you see. The current theory for electromagnetism isn't quantum. It's relativistic, baby! Relativistic quantum mechanics, and relativity basically demands that they both be the same force. Blah blah blah, one thing leads to another, and electromagnetism could be summarized in the absolute banger of an equation for the Lorentz force. There. F is equal to Q E plus V cross B. Look at this build. It's short, it's simple, much better than whatever mathematicians keep spewing at. Physicists, keep up the good work. B minus, that's because of the cross product masquerading as a multiplication there, but still, mwah, chef's kiss. And that equation, along with the knowledge we have of photons, actually summarizes practically everything when it comes to electromagnetism. And yeah, it might have been a fair bit confusing, that's because electromagnetism is basically the force that we arguably did the most research on as a species in the wildest amount of fields, and because of that, there are thousands of different models with thousands of different understandings, assumptions, oversimplifications, history, and inconsistencies, which are then difficult to straighten out, because I really can't stress enough, electromagnetism is probably the force with the largest impact as a whole. Like, yeah, the last force of this video may be the strongest and responsible for creation of basis of everything, but electromagnetism causes not only magnetism and electricity, but atoms, molecules, reactions, bonding, light, radiant energy, and the list goes on. That's why the segment for it was so long and was such a looming presence in this video, but I'll be honest, after this speech, I don't really know how to segue into the next chapter, because next we have weak force, which, well, at least we finally got a name that sticks. That's because weak interaction is a bit small. I mean, don't get me wrong, it's really interesting, it's just that it's mostly about decay. Or rather, beta decay to be exact. Alpha and gamma is a bit more electromagnetic and strong. Okay, so the gist of it looks like so. You have 6 quarks and weak interaction allows quark to swap between these options. That's it. So a quark can start as a top quark, which then can turn into a bottom quark, which in turn can decay into a charm quark. And okay, it's a bit cooler than it sounds, obviously. That's because if you consider that a neutron is just 3 quarks, 2 down, 1 up, and proton is 3 quarks, 1 down, 2 up. When a weak force turns that down into an up, then we turn a neutron into a proton using beta decay. So we take that neutron, we turn it into a proton, electron, and an antineutrino. It can also go the other way, so a proton can get turned into a neutron by emitting a positron and a neutrino. So you can see how this is, well, the exact opposite, with electrons, positrons, antineutrino, neutrino being antiparticle pairs. The weak force has some fun applications, fission being one of them, but what I'd like to focus on is its uniqueness in certain aspects. That is the way it breaks the CP symmetry, and the basic idea is that antimatter may decay into matter in this specific interaction, but the inverse is not possible due to a CP violation, which is kind of a big deal when you consider all the matter in our universe and the lack of antimatter. But now there is one last thing to mention, and that's the electroweak elephant in the room, the electroweak force. And like, I'd love to talk about the electroweak force, but even my sources are like, and I quote, Electroweak theory considers electromagnetism and the weak interaction to be different aspects of the same force. A key aspect of the theory is the explanation of why 3 out of 4 of the intermediary particles of the electroweak force are massive. The photon is the massive one. Unfortunately, the details of why this is are highly technical, so we cannot delve into this subject here. That's from the second part of a book in the university physics bookshelf on LibreText. I'm not a mathematician, I'm not a theoretical chemist, I'm not a nuclear physicist, and yet I've went through all 3 books on these topics to research this video, and none of them were as complex as this one. So hearing something like, the details of why this is are highly technical, well, it's kind of worrying, to say the least, you know. But don't worry, it's actually kind of simple. You just have the Higgs boson and the Higgs field, and the photon does not couple to Higgs field, and so no mass, because Higgs field creates mass. And oh, what is that? What is a Higgs field, and how does it relate to electroweak interaction? Don't worry about it, it's just normal physics research stuff that I'm certainly capable of understanding, because just basic relativistic quantum nuclear particle physics. Anyhow, that's kind of it for the weak force. It can turn quarks around, and because of that, it's responsible for decay. Also, because of some shenanigans at high energy with electromagnetism, it also might have something to do with creation of matter. It's highly technical, and I hope you can see what I meant now. It's certainly not only much weaker, but also much smaller, in the sense that it has a very narrow effect in comparison to something like gravity or electromagnetism. This effect, however, leads to a lot of interesting things, from decay up to mass itself. But then we have something which, whilst maybe not directly responsible for mass, it's kind of responsible for matter, and that is the strong force. Now, the majority of the strong force I will leave for the elementary particles video, since it will require a pretty decent knowledge of quarks, especially their color, since that's basically what it's about. So for now, I'll just say that almost, if not all of quarks' behavior can be attributed to the strong force. It is what causes the 3 quarks to make neutrons and protons. And it's actually so unbelievably strong that it's responsible for 99% of the mass of a proton. So in a proton, 1% of the mass is the quarks, 99 is the energy of the strong interaction, manifesting as mass. It's actually so strong that even though it should only be present in hadrons, so neutrons and protons, it literally just spills over them, causing something called residual force, or phrased in a clearer way, the nuclear force. That's how unbelievably strong the strong interaction truly is. When it comes to the nucleus of an atom, the electromagnetic interaction is trying to push all protons away, since, they're all positively charged, and it's the residual strong force, the part of the strong force that just spills over, the part that shouldn't even exist, that holds them together. You can imagine it like the almighty and powerful electromagnetic interaction, trying its hardest to push protons away, only for the strong interaction to stop it with a fraction of its power. However, this almighty being, the most powerful thing in our universe, is stuck, confined to the smallest scales. And so those are the 4 horsemen of the universe. First one, creating the basis of everything in the universe. Second, splitting into 2, for half of it to guide the powerful exchange between atoms, whilst the other watches over reactions and bonds, creating more and more complex structures to end up in the hands of the weakest horseman, the youngest sibling, the underdog that ends up shaping the universe. With its core might, these are the 4 horsemen of the universe. Hi, I'm MAKiT, the guy who made the video. Sorry if I sound a bit tired, it's just that I was supposed to finish this video 2 days ago. Anyway, if you've enjoyed this video, then I have some other ones, like this one, for example. Chemistry from a physical perspective. I also have a Discord server, if you'd like to come and chat. I have a Patreon, if you would like to support me. Thank you all so much to my Patreons. And I also stream every single day a series of live streams called Charity Checkups, which we're streaming for charity. Right now we're collecting money for Charity Prevent Cancer Foundation, and thank you everyone who donated. Anyhow, I think that's it. I have other videos to make, so I'm gonna go. just work on them. I also have to stream today. And for now, I suppose that'll be it. Thank you everyone so much for watching, and have a great day. Bye.